Today, we're diving into a story that honestly sounds like it's straight out of science fiction, but it's not. It's based on real data from a real experiment, and it's a discovery that might just force us to rewrite our most fundamental ideas about how the universe actually works. So, let me ask you a question. Picture this. You have a person's brain being monitored in a lab, and then thousands of kilometers away, there's a quantum computer just doing its thing. Now, there's no wire, no internet, no signal of any kind connecting them. Absolutely nothing. Could their activity possibly be linked? I mean, common sense, and frankly, all of physics as we know it, would scream, no way, impossible. But what if the data told a different story? And this is what that looks like. On one side, you've got the electrical signals from a human brain. On the other, the quantum state of a processor that is literally 8,800 kilometers away. According to everything we think we know, these two data streams should be completely random with respect to each other. They're totally separate, physically isolated systems. But as we're about to see, they're not. Not at all. So what happens when scientists actually compare the output from these two completely separate systems? Well, they found something that by all rights just shouldn't be possible. And this, right here, is the heart of the whole mystery. The patterns of activity from the brain and the quantum computer are, well, they're mirroring each other. And we're not talking about a vague similarity. The data shows a deep structural agreement. It's almost as if they were both reading from the exact same script, even though nobody gave them one. And here is the hard proof. So, a perfect correlation, a perfect match, is 1.0. In some of these sessions, the connection between the brain and the quantum system hit over 0.9. That is just an astonishingly strong link. It's way, way too high to be a coincidence. Even the average correlation was a pretty significant 0.36. This isn't just static or random noise. It's a real, measurable effect, and it demands an explanation. Okay, so how on earth is this possible? There's no physical connection, right? So the scientists had to look for a different kind of link, something hidden deep in the mathematics that could describe both systems. And what they found looks a lot like a secret blueprint. They found this single, incredibly elegant mathematical concept, which they called the intersection variable, or phi. The best way to think about phi is like a hidden architectural plan. It's not a physical thing you can touch, but it's a set of rules, a shared musical score that both the brain's neurons and the quantum computer's qubits seem to be following, all on their own. So here's how this blueprint seems to work. Imagine phi creating a kind of energy landscape, full of valleys or wells. Each one of these valleys represents a very specific pattern of activity. And here's the big discovery. This impossible connection only happens when both the brain and the quantum computer fall into the exact same valley at the exact same time. They have to be in a perfectly aligned state. So, okay, this shared blueprint, this phi thing, it seems to solve the mystery, right? It provides the common set of rules that lets these two totally isolated systems act together. So, case closed. Well, not quite. Not even close. Because finding that shared blueprint doesn't actually solve the problem. It just leads to an even deeper, way more profound question. A question that really starts to push the boundaries of what we even think of as science. This analogy just says it all. The blueprint, phi, that's the sheet music. It tells both the brain and the quantum computer what kinds of patterns are possible. But what it doesn't explain is how they manage to coordinate their timing so perfectly. How do they both decide to start on C# at the exact same millisecond if there's no conductor to give them to downbeat? Let's just be crystal clear on this. The blueprint explains the what, the shared library of possible states. But what it absolutely cannot explain is the when, that perfect, instantaneous, one-to-one matching of states across 8,800 kilometers of empty space. Something else has to be making that happen. And this is where the research takes a seriously radical turn. I mean, if the conductor isn't in the brain's orchestra and it isn't in the quantum computer's orchestra, then where could it be? The answer the data suggests fundamentally changes how we think about the act of observation itself. Okay, so this slide, this is the smoking gun. The data proves that the alignment between the two systems is a real, measurable event. The probability of it happening by pure chance is practically zero. And here's the critical part. The cause for this perfect alignment, it can't be found inside the brain, and it can't be found inside the quantum computer. It has to be coming from somewhere else. The lead researcher, Satoru Watanabe, put the mind-blowing conclusion right in the paper. He writes that this perfect alignment isn't created by some internal process, but is realized, and I quote, as an observation. In other words, the very act of a coherent observation taking place seems to be the thing that locks the two systems together. This leads to a truly revolutionary idea, the third observer, or O3. And we need to be very, very clear here. This is not a person or a consciousness or some cosmic being watching us. The paper proposes O3 as a fundamental, non-internal structure of reality. The best analogy is grammar. Grammar isn't a person, right? It's the underlying structure that's necessary for two people to have a coherent conversation. O3 is like the grammar of the universe that allows these separate systems to cohere. So this is the most important point to take away. This isn't metaphysics or philosophy. The paper is arguing that O3 is a necessary physical structure. Without it, the data that we are actually seeing, that statistically undeniable real-time connection, simply can't be explained. It's a new piece of our physical reality that the data is screaming for. The implications of this are, well, they're staggering. If this turns out to be true, it doesn't just add a new variable to our physics equations, it fundamentally redraws our entire map of the universe and our place in it. So here's the new map of reality the paper suggests. It's in 3 layers. The first layer is what they call relative. Just think of this as all the individual viewpoints, our brains, the quantum computer, you, me, each observing from its own perspective. The second, and this is the really groundbreaking layer, is the intersection. That's O3. This is that underlying grammar that allows all our separate viewpoints to line up and agree on a shared reality. And finally, there's the absolute layer, the fundamental background of existence that makes it possible for anything to be observed in the first place. So why does this all matter? It means observation isn't just a passive act of looking at a world that's already there. It's an active, physical process of creating coherence. It means the observer effect from quantum mechanics isn't just some weird little quirk. An observer as a structural condition is woven into the very fabric of reality. And maybe most profoundly, it means mind and matter aren't just two separate things that happen to be correlated. No, they are fundamentally linked through this shared, physical, observational structure. This changes the very foundation of how we do science. And this all leaves us with one final, huge, profound question. For centuries, we've thought of ourselves as passive spectators, just watching the universe unfold. But if this research is pointing in the right direction, observation isn't passive at all. It's a fundamental part of creation itself. It's the process that brings a coherent reality into existence. Which forces us to ask a pretty startling question. What reality are we, all of us, creating right now, just by looking?